The question we're really trying to answer in this video is how does the number of shared electron pairs affect the length and the strength of a covalent bond? And in order to answer this question, we first need to remind ourselves what a covalent bond is. The IB definition for a covalent bond is the electrostatic attraction between a shared pair of electrons and positively charged nuclei. And we might refresh our understanding by having a quick look at a diagram of this. So in this diagram you can see the blue arrows representing the electrostatic attraction between the two nuclei of the two atoms and the shared pair of electrons in between them. This is what's actually holding those atoms in place in this molecule. Because in this diagram we have only one shared pair of electrons, we'd call this a single bond. And we also need to be aware of double and triple covalent bonds. So let's have a look at an example of each and the impact of this on the length and strength of those bonds. For the example of a single covalent bond, let's take a molecule of chlorine. And if I drew a Bohr model diagram of a chlorine molecule, it would look something like this. And here you can see there's only one shared pair of electrons, which is why we call it a single bond. For the second example, let's consider an oxygen molecule which contains a double bond. Again, here is the diagram of an oxygen molecule. And in it, you can see that there are two pairs of shared electrons in the middle. Finally, let's take the example of nitrogen, more specifically a nitrogen molecule, which contains a triple bond. Here's a nice Bohr model diagram of that. And in this case, you'll notice there are now three shared pairs of electrons in the middle. Knowing the definition of a covalent bond, we should be able to predict the bond length and bond strength of these three molecules relative to each other. So you don't need to predict specific numbers, but comparatively. And if a covalent bond is the electrostatic attraction between the nuclei and shared pairs of electrons, well, if there are more electrons being shared, there's going to be more electrostatic attraction from the nuclei. I've represented greater electrostatic attraction with a thicker arrow between the nuclei of both atoms and the shared pairs of electrons. Understanding this, we would predict that I move from left to right across those three molecules. The bond length gets shorter because there's greater attraction between the nuclei and the shared electrons. Let's have a look at the actual data. And there you can see, yeah, it does follow that trend. The bond length gets shorter as the number of shared electrons increases. When considering bond strength, increased electrostatic attraction between the nuclei and shared electrons would be expected to strengthen bonds. So as I move from left to right, I would expect to see the bond strength increase. Let's have a look at the data. Again, you can see a nice trend appearing from left to right. In this case, the bond strength is increasing. And as a quick reminder, those numbers for bond strength are the kilojoules per mole required to break that bond. Let's now summarise the key points from this video. Very simply, the more shared electron pairs there are in a covalent bond, the more electrostatic attraction there will be between that electron pair and the nucleus. And if there's more electrostatic attraction between the nuclei and the shared electrons, a bond will be shorter and stronger. The key concept here, as with much of chemistry, is the idea of electrostatic attraction, and it's important to use that term in answers to exam questions. Hopefully, this video is of some help.